You were told Pluto was a frozen nobody at the edge of the solar system, a demoted ice ball not worth thinking about. Then NASA spent 9 years chasing it with one of the fastest spacecraft ever launched, betting that this tiny world, smaller than our moon, was hiding something big. When New Horizons finally flew past, the data that came back hit scientists harder than anyone expected, and quietly blew a hole in the old story of what small and far away are supposed to mean. In this video, you're going to see why Pluto went from punchline to paradox, how a so-called dwarf planet forced experts to rewrite their models, and what that means for every distant, cold world we've been underestimating. But before we continue, please subscribe to the channel to give your support. Let's continue. Start with the basic numbers. Pluto is about 2,377 kilometers across, roughly 1/5 the diameter of Earth, and smaller than our moon. In miles, that is just under 1,500. It orbits almost 40 times farther from the sun than Earth does. The surface temperature is around 40 Kelvin, about minus 233 degrees Celsius or minus 387 degrees Fahrenheit. The air is barely an atmosphere. At the surface, the pressure is around 10 to the minus 5 bar, about 100,000 times thinner than the air you are breathing. At those pressures and temperatures, nitrogen, carbon monoxide, and methane do not behave like they do on Earth. They easily freeze into solid ice and sit on the ground. Put all of that together, and the old prediction is simple. A tiny body with low gravity, far from the sun, with a thin atmosphere and very little tidal heating should cool down fast and lock up. The interior freezes, the crust stiffens, and geological activity shuts off. Impacts carve craters, but there is no volcanism, no plate tectonics, no weather system strong enough to repaint the surface. Pluto turns into a time capsule from the early solar system that has hardly changed in billions of years. That is how Pluto was usually described before 2015, a cold fossil, interesting mainly as a record of formation, not as a world doing anything new. So if the physics says Pluto should be frozen and done, why did NASA aim one of the fastest spacecraft ever built at it and spend almost a decade getting there? To reach Pluto in a useful time, you could not just drift outward. NASA launched New Horizons in January 2006 on an Atlas V rocket and pushed it harder than any probe before it. Relative to Earth, it left at about 16.3 kilometers per second, around 58,000 kilometers per hour. That made it the fastest Earth departure in history at the time, because the goal was to reach Pluto while the mission team was still around to receive the data. For most of its 9-year journey, Pluto was just a speck. As New Horizons closed in during early 2015, the images sharpened step by step. Dark bands appeared around the equator. Bright areas showed up in the middle of the disk. Already, the surface looked more complex and old and cratered. On the 14th of July 2015, New Horizons made its closest approach, skimming just 12,500 kilometers above Pluto's surface. It was moving at about 13.8 kilometers per second relative to Pluto, nearly 50,000 kilometers per hour. At that speed, it crossed a distance equal to Pluto's diameter in under 3 minutes. There was no way to slow down, no second pass, no orbit. The entire mission at Pluto depended on a single flyby. That short window was enough to destroy the old picture. In the first full-frame, high-resolution images that came down, one feature dominated everything. A huge, bright, heart-shaped region front and center, covering a large part of one hemisphere. You did not need to be a scientist to see how odd that was. That heart is now called Tombaugh Regio, after Clyde Tombaugh, Pluto's discoverer. Its western half, Sputnik Planitia, is even more surprising. It's a gigantic basin, roughly 1,400 kilometers long and about 1,200 kilometers wide, almost the size of Western Europe, filled with nitrogen ice with traces of carbon monoxide and methane ice. In miles, that's about 870 by 750. Here's the key point. When you zoom in on Sputnik Planitia, you do not see a landscape that has been sitting unchanged for 4 billion years. You see a surface that is smooth, patterned with large polygon-shaped cells, and almost completely lacking in impact craters. Craters are your clock in planetary science. If a surface is old, it will be covered in them. If it's young, something has erased them. On Sputnik Planitia, the crater count is so low that the best estimate for the surface age is between roughly 10 million and 100 million years. The leading explanation is that the nitrogen ice in this basin is slowly flowing and overturning, like a very slow glacier. Slightly warmer material from deeper layers rises, cooler material sinks, and the surface is constantly renewed. This process, called solid-state convection, can run at just a few centimeters per year and still erase craters over tens of millions of years. So now you're staring at a paradox. A tiny, distant dwarf planet is somehow running a huge, active nitrogen ice sheet that keeps itself young. That doesn't fit the original dead fossil model at all. And the moment you accept that Pluto is not dead, one more question hits you, and this is the part that really shook scientists. If Pluto, with a mass of only 1.2 times 10 to the 22 kilograms, sitting roughly 39 times farther from the sun than Earth, can keep this level of activity going, what does that say about the rest of the outer solar system? Pluto is not the only object out there. It's one of a large population of icy bodies in the Kuiper Belt, many of them in the same size range, from a few hundred to a couple thousand kilometers across. If even one of them can have glaciers, young plains, a changing atmosphere, and maybe a hidden internal ocean, then a lot of those minor bodies might be fully developed worlds too. That's the real impact of what NASA found at Pluto. New Horizons didn't just send back images of a demoted planet. It took a simple idea that small, cold, distant objects are simple and dead, and proved that idea wrong in a single flyby. Pluto answered with a bright, active heart of nitrogen ice and a surface that refuses to match the old expectations. And if the very first close look at Pluto could overturn that much of the standard story, what else is hidden in the way we got there? In the extreme speed, the gravity assist, and the one-chance trajectory that had to be perfect. How do you even hit a target that is 5.9 billion kilometers away, so small that it would fit under a fingertip at arm's length, and moving through space the whole time you are chasing it? If Pluto was going to overturn everything scientists thought about small frozen worlds, New Horizons first had to do something just as crazy. It had to get there fast enough that the mission would still matter. To beat the clock, you need speed that sounds almost unreasonable. When New Horizons launched in January 2006, it rode an Atlas V rocket and left Earth going about 16.3 kilometers per second relative to the planet. That is around 58,000 kilometers per hour, roughly 36,000 miles per hour. No spacecraft had ever left Earth that fast before. You were basically throwing a probe the size of a small piano away from the Earth at more than 40 times the speed of a passenger jet. Why push that hard? Because if you went slower, Pluto would win by simple patience. Its orbit is so far out that a cruise at typical interplanetary speeds would put your arrival date in the late 21st century. The people who planned the mission would be gone. The technology to receive the data might even be obsolete. So the team made a trade. Go fast, accept that you can never slow down and orbit Pluto, and designed the whole mission around a one-time high-speed flyby. But even that record-breaking launch speed was not enough on its own. You still need an extra kick to cut years off the trip. That is where Jupiter comes in. In early 2007, barely a year after launch, New Horizons dived toward Jupiter and passed at a distance of about 2.3 million kilometers, roughly 1.4 million miles. That is close on the scale of a giant planet. Here's the key idea. Jupiter is not just a big ball of gas. It's a moving source of gravity with a mass about 1.9 times 10 to the 27 kilograms. When New Horizons fell into its gravity well and then climbed back out, timed so it exited in the direction of Pluto's orbit, it stole a tiny bit of Jupiter's orbital energy. The probe gained about 4 kilometers per second of extra speed, roughly 14,000 kilometers per hour, around 9,000 miles per hour, without burning a drop of fuel. That gravity assist shaved about 3 years off the timeline. Without it, you'd be looking at a flyby in the late 20-teens instead of 2015. With it, the mission became a 9-year sprint through the outer solar system instead of a 20-year wait. So what does a 9-year sprint actually look like? By the time New Horizons reached Pluto in July 2015, it had traveled around 4.8 billion kilometers since launch, about 3 billion miles. Its distance from the sun was such that light itself, moving at 300,000 kilometers per second, took about 5.5 hours to go from the sun to Pluto. A radio signal from the spacecraft back to Earth needed the same 5.5 hours one way. That delay changes how you run a mission. You cannot joystick a spacecraft when every command takes more than 11 hours for a round trip. You cannot wait to see an image, decide to turn a camera, send the instruction, and expect it to arrive in time. By the time you react, Pluto is already behind you. That brings you to the most brutal constraint New Horizons faced, the one-shot nature of the encounter. At closest approach, the probe was moving at about 13.8 kilometers per second relative to Pluto, nearly 50,000 kilometers per hour, about 30,000 miles per hour. At that speed, it crosses the entire width of Pluto in under 3 minutes. That's less time than it takes you to boil water for coffee. So the team had to lock in everything months in advance. Every turn of the spacecraft, every exposure time on every camera, every moment when an instrument would look at Pluto, at Charon, at the small moons, all of it was scripted and loaded into the onboard computer long before arrival. If one pointing sequence had been wrong, if one timing assumption had been off, you would not get a second pass to fix it. The first close look at Pluto was also the only close look you were going to get for decades. You might think that once the flyby was over, the hard part was done. It was not. Even after a perfect pass, you don't just download Pluto like a file over fast home internet. At a distance of roughly 5 to 6 billion kilometers from Earth, the data rate from New Horizons was only about 1 to 2 kilobits per second. That's a bit or two per millisecond. Old dial-up internet in the 1990s was much faster than that. The spacecraft stored its images and measurements on solid-state recorders, and then slowly trickled them back to Earth, day after day. It took around 15 months to send everything home. Mission Control would schedule long tracking passes with the giant radio dishes of the Deep Space Network, stare at a faint, steady stream of bits coming in from the edge of the solar system, and slowly, frame by frame, build up the full picture of Pluto and its moons. So now you have a clear picture of the stakes. To even get one sharp image of Pluto's surface, you had to launch the fastest probe ever sent from Earth, hit a moving gravity assist with near-perfect timing, run a blind pre-programmed flyby at almost 14 kilometers per second, and then wait more than a year for the data trickle to finish. And after all that effort, the first global images come down and show that the tiny world at the end of this insane journey is not a fossil at all, but a geologically active body with a bright young heart of nitrogen ice. If the journey itself needed that much precision and endurance, what does that say about the world that justified it? What kind of planet forces you to work this hard just to learn that your basic idea of small and frozen was wrong? After all that effort to reach Pluto at insane speeds, the obvious question is, what exactly did we hit? A dirty snowball, a big comet, or something that behaves much more like a real planet? Start with the hard numbers, because they already tell you Pluto is not a simple object. Its radius is about 1,185 kilometers, so a bit over 700 miles. That gives you a diameter of about 2,377 kilometers. Its mass is around 1.3 times 10 to the 22 kilograms, which is roughly 1/6 the mass of our moon. From those two numbers, you get a density of about 1.9 to 2 grams per cubic centimeter. In plain words, Pluto is almost twice as dense as pure water ice, but clearly not as dense as a rocky planet like Earth. That density matters because it gives you a first clue about what Pluto is made of. If Pluto were just a big lump of frozen gases and water ice, its density would be much closer to that of ice, around 1 gram per cubic centimeter. If it were mostly rock, it would be up near 3. Sitting in between tells you straight away, you're dealing with a mix, not a pure material. You're looking at something that is neither a classic rocky planet nor a simple ice ball. Now take a moment and put yourself on the surface because gravity there feels very different from what you're used to. Pluto's surface gravity is about 0.058 g, so only 5.8% of Earth's. If you weigh 80 kilograms on Earth, the scale on Pluto would barely read 5 kilograms. In pounds, a person who weighs 176 pounds here would feel like they weigh around 11 pounds there. A strong jump on Pluto would send you much higher and slower than on Earth, and you would fall back down in lazy slow motion. The escape velocity, the speed you need to leave Pluto and never fall back, is only 1.1 kilometers per second, around 2,500 miles per hour. For comparison, getting off Earth takes about 11.2 kilometers per second. That low escape speed is why Pluto struggles to hang on to light gases, and why its atmosphere leaks into space over time. So the numbers already say low gravity, mixed composition, weak hold on its atmosphere. But what does that mixed composition actually look like inside? Is Pluto just a pile of random stuff, or is it a structured world? Here is where that density value becomes more than a statistic. Around 2 grams per cubic centimeter is too dense for a pure ice body, and too light for a fully rocky one. The most straightforward model that fits is a roughly 2-to-1 mix of rock and ice by mass. That means a rocky core in the center carrying most of the mass, wrapped in a thick mantle of water ice, and then coated near the surface with a much thinner layer of more volatile ices, mainly nitrogen, methane, and carbon monoxide. In other words, the hard rock of Pluto is water ice, acting as structural material at those temperatures, and the bright, mobile stuff you see on the surface, that heart and those planes, are a relatively thin skin of frozen gases. This layout is important because that rocky core is where most of the heat from radioactive decay lives, and that heat is what may keep a subsurface ocean from freezing solid. Already, from density alone, you're forced to treat Pluto as a differentiated, layered world, not as a random frozen clump. But composition is only half of the story. How this world spins and tilts also matters, because that controls its seasons and climate. Pluto rotates once every 6.387 Earth days, so its day is just over 6 1/3 of our days. That is already slow compared to Earth's 24 hours. But the tilt is what really breaks expectations. Pluto's rotation axis is tilted by about 120 degrees relative to its orbit. That means it is effectively tipped past sideways. If you think of Earth as a spinning top leaning a little, Pluto is one lying almost on its side, even more extreme than Uranus. This huge tilt means extreme seasons. One pole can spend decades pointed toward the sun in a long, dim summer, while the other pole sits in continuous darkness. Then, over its 248-year orbit, that situation slowly reverses. For a world covered with volatile ices that can melt, freeze, and sublimate at just a few degrees change, this tilt is not just a detail, it drives where the nitrogen and methane migrate, when the atmosphere thickens or thins, and how regions like Sputnik Planitia act as cold traps. So you have a small, layered world with a slow spin and a wild axial tilt. Now add one more key piece. Pluto does not live alone. It's locked in a tight dance with its largest moon, Charon, and that relationship is so unusual that it changes how you classify the system. Charon's radius is about 606 kilometers, a bit under 400 miles, roughly half the size of Pluto. Put Pluto and Charon side by side, and together they would barely stretch across the continental United States. Charon is so large relative to Pluto that their common center of mass, the barycenter, actually lies outside Pluto's surface. That's not how the Earth-Moon system works, and it's not how most planet-moon systems work. Dynamically, Pluto and Charon are closer to a double world than a classic planet with a small satellite. Both Pluto and Charon are tidally locked to each other. Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. In the past, while that lock was forming and their orbits were still evolving, tides between them would have flexed both bodies, generating heat inside. Today, their orbits are nearly circular and the tidal heating is much weaker. But the long history of that interaction may have helped melt internal ice, start an ocean, and keep some internal heat going much longer than you would expect for such small bodies. So you have a small, layered world with a slow spin and a wild axial tilt. Now add one more key piece. Pluto does not live alone. It's locked in a tight dance with its largest moon, Charon, and that relationship is so unusual that it changes how you classify the system. Charon's radius is about 606 kilometers, a bit under 400 miles, roughly half the size of Pluto. Put Pluto and Charon side by side, and together they would barely stretch across the continental United States. Charon is so large relative to Pluto that their common center of mass, the barycenter, actually lies outside Pluto's surface. That's not how the Earth-Moon system works, and it's not how most planet-moon systems work. Dynamically, Pluto and Charon are closer to a double world than a classic planet with a small satellite. Both Pluto and Charon are tidally locked to each other. Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. In the past, while that lock was forming and their orbits were still evolving, tides between them would have flexed both bodies, generating heat inside. Today, their orbits are nearly circular and the tidal heating is much weaker. But the long history of that interaction may have helped melt internal ice, start an ocean, and keep some internal heat going much longer than you would expect for such small bodies. So Pluto is not just a small object, it's one half of a binary system, with Charon carrying its own record of tectonics and resurfacing. That again pushes you away from the big comet label and into complex planetary system territory. Now zoom out one more step, because Pluto is not a one-off oddball, it's part of a family. Beyond Neptune, you have the Kuiper Belt, a wide region filled with icy bodies, many of them roughly 1,000 kilometers across or more. Objects like Eris, Haumea, and Makemake live in the same general zone, and many exoplanets we see around other stars fall into the same size and temperature range as Pluto. This is where New Horizons change the stakes. Before the flyby, Pluto could be written off as a weird, demoted former planet. Afterward, it became the reference case. If Pluto, a typical Kuiper Belt object, has a layered interior, real geology, a dynamic atmosphere, and maybe an internal ocean, then you have to treat other similar bodies here and around other stars as potential complex worlds too. So when you hear dwarf planet or Kuiper Belt object, the basic simple image of a frozen, inactive ice ball no longer works. The basic physical numbers, radius, mass, density, gravity, spin, tilt, and its binary partner all point in the same direction. Pluto is not a big comet that somehow got promoted. It's a small, fully developed world at the edge of the solar system. And once you accept that, you're forced to ask a much harder question. If even the bulk structure is this complex, what's happening on the surface, in that giant heart of nitrogen ice that should not be active at all? How can the coldest, brightest patch on Pluto be the part that looks most alive? When New Horizons sent back the first sharp global image and that big pale heart came into focus, it wasn't just cute. It was a red flag to every scientist who thought Pluto was geologically dead. That heart is Tombau Regio, and its left half is the real troublemaker, Sputnik Planitia. You're looking at a vast basin roughly 1,400 kilometers long and about 1,200 kilometers wide, so around 870 by 750 miles. It's filled with not rock, but with frozen nitrogen, with some carbon monoxide, ice, and methane mixed in. That makes it, as far as we know, the largest single glacier in the solar system, bigger than anything in Antarctica, bigger than any ice sheet on Mars. A continent-sized slab of frozen gas sitting on a dwarf planet. So here's the problem. A glacier that big should, on a dead world, be old, beaten up, covered in impact scars. But when you zoom in, that's not what you see at all. Why does this huge plain look so clean if it's been sitting there for billions of years? When scientists counted craters on Sputnik Planitia, they found almost none. On a world as exposed as Pluto, impacts are constant over long timescales. If a surface is 4.5 billion years old, it'll be absolutely littered with craters of all sizes. On Sputnik Planitia, the number of craters is so low that the best estimates for the surface age fall between about 10 million and 100 million years. On solar system timescales, that is basically brand new. Some individual patches may be even younger, close to geologically now. This means something is constantly wiping the surface clean, covering old impacts, smoothing out the scars. On Earth, you would blame plate tectonics or thick lava flows. On Pluto, you cannot use those excuses so easily. So what is doing the resurfacing here on a world this cold and small? When the team analyzed the patterns on Sputnik Planitia, they saw the key clue: a network of big, irregular polygon shapes, tens of kilometers across. Each cell is slightly higher in the middle and lower at the edges, and surface cracks tend to form along the boundaries. That is exactly what you expect when a material is slowly rising in the center of each cell and sinking at the edges, overturning over and over. In other words, the nitrogen ice in Sputnik Planitia is not just sitting there, it is convecting. The layer is probably a few kilometers thick, and heat from Pluto's interior, even though it is weak, is still enough to make slightly warmer, slightly less dense ice rise, and cooler ice sink. The flow speeds are tiny, centimeters per year, but over tens of millions of years, that is more than enough to drag old craters down and bring fresh material up, resetting the surface like a slow, frozen conveyor belt. Here's the paradox. How is a dwarf planet with almost no ongoing tidal heating able to keep a nitrogen ice sheet kilometers thick moving like this? That is exactly the kind of process you expect on places like Earth or Io, not on a body where the average surface temperature is around minus 235 degrees Celsius, about minus 390 degrees Fahrenheit. And the surprises do not stop at the patterns on top. What happens when you look at the basin shape and the land around it? New Horizons stereo images and topography maps show that the central part of Sputnik Planitia sits about 3 to 4 kilometers lower than the surrounding uplands, around 2 to 2.5 miles. The rim is broken and rugged, with blocks of water ice bedrock standing above the plains like islands, and the interior is dotted with pits and troughs that look like places where nitrogen has slowly sublimated away. Even more shocking, in the western part of the basin, near the boundary with those water ice highlands, you see features that look like dunes. Long, parallel ridges and dark streaks appear, consistent with methane ice particles being pushed into lines by winds blowing across the plain. The grains themselves are probably only a few hundred micrometers across, like very fine sand. The local winds might only reach a few meters per second, a gentle breeze by Earth standards. But in Pluto's low gravity and thin air, that's enough to move particles and build dunes over time. So now you have three things happening in the same place: a deep impact basin, a thick nitrogen glacier overturning inside it, and winds sculpting the surface into dunes. Ask yourself honestly, does that sound like the surface of a frozen fossil or like an active environment, even if everything is running in ultra slow motion? All of this leads to one more key question. Is Sputnik Planitia just a passive layer of ice responding to Pluto's environment, or is it actually driving Pluto's environment? Models that combine the shape of Pluto's surface, the depth of Sputnik Planitia, and the properties of nitrogen ice point toward a striking answer. As the sun slowly rises and sets over this basin each Pluto day, the nitrogen at the surface warms slightly and starts to sublimate, turning from solid directly into gas. When night comes, that gas can refreeze elsewhere or condense back onto the plane. This daily cycle of sublimation and refreezing doesn't just rearrange frost, it pumps nitrogen into and out of Pluto's thin atmosphere. Because Sputnik Planitia is so large and so low, it acts as a massive cold trap and source at the same time. The result, according to climate models, is that pressure gradients build up between the basin and higher ground, driving winds that blow predominantly westward along the equator. Those winds can actually run opposite Pluto's rotation, fighting against the direction the surface is turning underneath them. So this bright heart is not just a cosmetic feature on Pluto's face, it's a mechanical system, a kind of atmospheric engine that helps organize global circulation. It influences where haze and frost build up, how methane and nitrogen are distributed, and where erosion and deposition are strongest. Change Sputnik Planitia, and you change Pluto's climate pattern. Put all of this together, and you get a very uncomfortable conclusion for the old textbook view. A dwarf planet, smaller than our moon, sitting nearly 40 times farther from the sun than Earth, is running the largest glacier in the solar system, with active convection, deep basins, dunes, and a volatile cycle powerful enough to steer its winds. Once you accept that, you have to ask the next hard question. If frozen nitrogen can flow like this, what is holding up those jagged 3 to 4 kilometer high mountains just next door, in an atmosphere this thin and a temperature this low? And what does that say about what counts as rock on Pluto? How do you get mountain ranges the size of the Alps on a world that's supposed to be made of ice? When you look at the edge of Sputnik Planitia, that bright nitrogen plain, you don't just see a flat sheet. You see jagged walls, towers, and ridges, 3 to 4 kilometers high, sitting right next to that smooth glacier on a dwarf planet with only about 6% of Earth's gravity. New Horizons flew over that boundary and picked out entire mountain ranges with names like Tenzing Montes and Hillary Montes. These peaks rise roughly 3 to 4 kilometers above the surrounding plains, so about 10,000 to 13,000 feet, very similar in height to the Alps or the Rockies back on Earth. That alone is already strange. You're getting Earth-sized mountains on a body that is smaller than our moon, in air so thin you would call it near vacuum, at temperatures around 40 Kelvin, which is about minus 233 degrees Celsius or minus 387 degrees Fahrenheit. You might think, fine, low gravity makes it easier to stack material high, so maybe that is all there is to it. But then you ask, what is actually holding those mountains up? The stuff that makes the plains, nitrogen ice, is soft and flows under its own weight even at these temperatures. If the mountains were made of the same material, they would slowly sag and flatten over time. They would not keep sharp peaks and steep faces. The answer is that Pluto forces you to flip your definition of rock. At around 40 Kelvin, water ice is not a weak, slippery solid the way you know it on Earth. It is as strong as granite. The plains of Sputnik Planitia are covered mainly in nitrogen ice, which behaves like a weak, creeping material. The mountains, in contrast, are blocks of rigid water ice, the real structural bedrock of Pluto, poking up through the softer nitrogen layer. So when you see these ranges, you're basically looking at water ice continents standing above a sea of frozen nitrogen. That alone would be impressive. Big, stable blocks of water ice forming mountain chains in ultra-cold air. But then you move your eye away from the immediate edge of Sputnik Planitia and notice other, even stranger shapes. Enormous shield-like mounds with broad bases and central pits that do not fit the pattern of normal impact craters or simple tectonic blocks. The most famous of these is Right Mons, and another likely example is Picard Mons. Right Mons is roughly 150 to 200 kilometers across, about 90 to 120 miles, and around 4 kilometers high, so about 13,000 feet. Its flanks are irregular and hummocky, made up of lumpy, uneven terrain, and at the summit there is a large central depression, not a sharp peak. Picard Mons shows a similar shield shape, though the details are less clear. On Earth, when you see a broad, low cone with a central depression and rough, flow-like textures on the sides, your first thought is volcano. The difference here is that on Pluto, at these temperatures, you are not dealing with molten rock. The best explanation that fits the shapes and the context is cryovolcanism, volcanoes that erupt cold materials, like water, ammonia-rich slush, or other mixed ices instead of lava. In that picture, Right Mons is a cryovolcano built by repeated eruptions of icy material that piled up over time, leaving a summit pit where the source emptied out or collapsed. To get a sense of scale, the total volume of material in one of these constructs could be comparable to a major volcanic edifice on Earth, something in the league of the big shield volcanoes in Hawaii, but assembled from frozen water and volatiles instead of basalt. That's not a small local feature, that's a massive investment of internal energy. So now you have mountain ranges of hard water ice, plus huge shield-like features that look very much like cryovolcanoes. The next obvious question is, how old are these structures? Did this activity happen in Pluto's deep past, or did it continue until relatively recently? When you look closely at the flanks of Right Mons and similar features, one thing jumps out. You see very few impact craters. That's not what you would expect if the surface had been sitting quietly for 4 billion years. Over that amount of time, random impacts should pepper the slopes with craters of all sizes. The lack of craters suggests that these terrains are geologically young. The current estimates say they are probably less than about 1 billion years old, and some parts could be much younger than that. If that is correct, then Pluto has not just been active in some distant, mysterious early phase. It has been doing serious geology well into recent geological time. You are not looking at a single frozen accident. You are looking at a world that has, in the last billion or less, pushed large volumes of material up from its interior, reshaped its surface, and maintained tall, rugged topography. At this point, the big, uncomfortable question is obvious. Where is Pluto getting the energy for this? On Io, the intense volcanic activity is powered by strong tidal flexing from Jupiter. On Europa, or Enceladus, tidal heating from their giant parent planets pumps energy into their interiors and keeps their oceans liquid. Pluto doesn't have that luxury. Pluto and Charon are tidally locked, facing each other with the same sides, and their orbits are almost circular, so there is very little ongoing tidal flexing left. You can't rely on a giant nearby planet shaking Pluto and keeping it warm. That leaves you with more subtle sources, primarily the heat stored from Pluto's formation and the slow release of energy from radioactive decay in its rocky core. At first glance, that doesn't sound like much, especially over 4.5 billion years. But Pluto has a thick, insulating shell of water ice and volatiles. Once you bury heat under that shell, it leaks out very slowly. If the interior composition is right and the ice shell is the right thickness, that modest energy budget can still be enough to keep parts of the deep interior warm, to drive long-term convection, and to allow pockets or layers of liquid to survive under the crust. So here's the bigger implication. If Pluto, with no strong current tidal heating, can still build cryovolcanoes and maintain huge mountains of water ice, powered mostly by radiogenic heat and leftover formation energy, then a lot of other small worlds distant everywhere else around the Sun and around other stars may be running a slower version of the same engine, with interior oceans, long-lived heat, and active surfaces. Once you see mountains made of water ice and cryovolcanoes erupting icy material on a world this small and cold, you are forced to ask the next question. If the crust is still moving and erupting, what is underneath it? And could there really be a hidden ocean deep below Sputnik Planitia, massive enough to pull an entire basin toward Charon and crack the planet's surface open? Why does Pluto's biggest impact basin sit in exactly the wrong place if it really is just an empty hole? A normal impact crater removes mass, so you expect a negative weight there. But Sputnik Planitia refuses to behave like a normal crater, and that's the first sign something deep inside Pluto is not what you thought. Start with the simple expectation. A big impact hits Pluto, blasts out a huge chunk of crust, and leaves behind a deep basin. You've removed material, so the local gravity should be slightly weaker than average, a negative mass anomaly. Over long times, a spinning body tends to rotate so that heavy regions migrate toward the equator or toward the line joining it to its main companion, and light regions migrate away. Empty holes should drift off those preferred positions. On Pluto, you see almost the opposite. Sputnik Planitia sits very close to the tidal axis, the line that runs from Pluto's center through the point that faces Charon. Instead of a missing mass moving away from that axis, you appear to have an extra mass that has actually been pulled toward it. In other words, the basin behaves like a positive mass anomaly, a gravitational weight, not a deficit. So you have a paradox. The shape screams impact crater. The orientation and the way Pluto seems to have reoriented around it says heavy region anchored toward Charon. How can a hole in the crust act like an extra weight? One way out is to assume the cold nitrogen ice filling the basin is somehow enough to turn a negative into a positive. But the density of nitrogen ice is lower than that of water ice, and much lower than rock. Replacing rock and water ice with nitrogen should not make the region heavier, it should make it lighter. The more you push that idea, the worse it fits. That is where the subsurface ocean comes in as the missing piece. When you combine New Horizons measurements of Pluto's shape, the depth estimate for Sputnik Planitia, and the way the basin is oriented relative to Charon, models keep pointing to the same solution. There is an extra layer of relatively dense material at depth, directly under the basin. The best candidate is a global or near global ocean of liquid water mixed with ammonia or salts, lying under the outer ice shell. If part of that shell thinned beneath Sputnik Planitia and the water layer there moved upward a bit, you would replace lower density ice with higher density liquid water and brines. That change would create a positive mass anomaly, exactly the kind of weight that could slowly drag the basin toward the tidal axis over millions of years. In those models, the ocean could be on the order of 100 kilometers thick, sitting beneath an ice shell that is thinner under Sputnik Planitia and thicker elsewhere. In miles, you're talking about a liquid layer around 60 miles deep under a solid lid perhaps a few tens of kilometers thick in that region. That is not a tiny pocket. That is a planetary scale structure. So now the question is not just, did Pluto once have an ocean, but how much of that ocean is still liquid today, and what has it done to the crust over time? Liquid water creates another problem for the old frozen fossil picture when you think about what happens as it cools. Unlike most materials, water expands when it freezes into ice. If Pluto started with a larger liquid layer and it has slowly been freezing from the top down and maybe from the bottom up, the total volume of the solid ice shell would increase. That expansion pushes outward on the crust. What does a rigid shell do when something deep inside tries to stretch it? It cracks. On Pluto, New Horizons saw exactly the kind of features you would expect from global stretching: long, wide chasms and troughs, hundreds of kilometers long, and in some cases several kilometers deep, cutting across the surface. These are extensional tectonic structures, not compressional ones. They look like a crust that has been pulled apart, not squeezed. So you have three linked clues: a heavy basin near the Charon-facing side, a need for denser material at depth to explain that, and global-scale fractures that fit an expanding shell over a freezing interior. Together, they point strongly to a subsurface ocean that has existed for a long time and has been freezing gradually, reshaping Pluto's outer shell as it does. That raises the next hard question. How can liquid water survive inside a body this small, this far from the sun, for billions of years? At Pluto's distance, around 39 times farther from the sun than Earth, sunlight is weak and the surface temperature stays around 40 to 50 Kelvin. There is no way surface heating alone can keep water liquid deep below. The key is insulation and internal heat. Pluto's thick ice shell, made mostly of water ice with a cap of volatile ices, is a very poor conductor of heat. Once you bury an ocean under tens or hundreds of kilometers of ice, heat leaks out only slowly. Inside the rocky core, radioactive elements like uranium, thorium, and potassium decay over time, releasing energy as heat. Even at a modest rate, over 4.5 billion years, that heating can be enough when trapped under a good insulating blanket to keep a substantial layer of water from freezing solid. Add in the fact that any ammonia or salts mixed into the water will lower its freezing point, and suddenly it's not so crazy that Pluto could preserve a partially liquid ocean at temperatures around minus 200 degrees Celsius at the base of the ice shell. It doesn't need to be warm by human standards. It just needs to be slightly above its local freezing point. Once you accept that basic argument, the implications move beyond Pluto. If a body with Pluto's mass and size can hold on to a deep subsurface ocean for most of solar system history, then you have to consider that many other icy worlds of similar scale in the Kuiper Belt and even around other stars might be doing the same thing. Subsurface oceans stop being rare exceptions like Europa or Enceladus and start looking like a common outcome for icy bodies with rock in their cores. That leads straight into the next hard shift. What does this do to your idea of where potentially habitable environments can exist? No one is seriously claiming life on Pluto based on current data, but take the ingredients seriously. You have a deep, salty ocean in contact with a rocky core, which means water can interact with rock and produce interesting chemistry. Above that, you have an ice shell rich in organics, constantly bombarded by radiation that breaks molecules apart and forms complex new ones. Some fraction of those products may be transported downward over time. That's a layered system with energy sources, chemical gradients, and long timescales, all buried under an ice shield that protects it from the harsh vacuum and radiation outside. It's not Earth-like, and it doesn't fit the classic picture of a habitable zone around the star, where liquid water is supposed to exist only on the surface in a narrow band of temperature. Pluto forces you to stretch that map. It says that if you only look for oceans on the surfaces of Earth-sized planets in the comfortable zone around the star, you're probably missing a huge population of hidden oceans inside small, distant worlds. Many of those worlds will never see direct sunlight on their liquid water, but they may still run complex chemistry for billions of years. And if a demoted dwarf planet at minus 230 degrees Celsius can hide an ocean large enough to tug an entire basin toward its moon and tear its own crust apart, what else is hiding further out in the Kuiper Belt? And how strange does Pluto's thin, blue, haze-filled sky have to be to sit on top of all of this? How can a world with almost no air still have a real sky? Pluto's surface pressure is only around 10 microbar, roughly 100,000 times thinner than the air you're breathing right now. You could never breathe it, you'd need a spacesuit, and yet it's thick enough to run temperature gradients, hazes, and even winds that shape the ground. Stand on Pluto and the air around you is mostly nitrogen gas, the same main ingredient as Earth's atmosphere, but stretched out into an incredibly thin layer. Even so, gravity is low, so that tiny amount of gas can extend far upward. New Horizons measured the pressure by watching how the signal from Earth bent and faded as the spacecraft slipped behind Pluto. That told scientists that this is not just a trace of gas, it's a real structured atmosphere. The shock comes when you look back toward the sun through this thin shell. In the backlit images from New Horizons, when Pluto was a dark disk in front of the sun, the edge of the planet glowed with a clear blue ring. That ring is not a camera trick, it's Pluto's sky. So what's actually in that ring if the gas is so thin? When scientists processed the images, they found that Pluto's atmosphere is not just a smooth haze, it's layered. You can count at least 20 distinct haze layers stacked like faint, uneven sheets, reaching more than 200 kilometers above the surface, maybe up to 300 kilometers in some places. That's about 120 to almost 200 miles high for a small world. Those layers are not made of gas, they're made of tiny solid particles, complex hydrocarbons called tholins. They form when ultraviolet light from the sun hits the methane and nitrogen in Pluto's atmosphere and breaks those molecules apart. The fragments are reactive. They stick together in new combinations, building long chains and ring structures, moving from simple methane and nitrogen toward darker, more complex organics. As they grow, they lose the ability to stay as isolated gas molecules, and they start to behave like solid or liquid droplets suspended in the air. These particles are small enough that when sunlight hits them, they scatter blue light more efficiently than red, giving the atmosphere that bluish tint in the backlit images. It is the same basic physics that makes Earth's sky blue, but working in a much thinner gas with a much higher fraction of solid haze mixed in. So you have a thin nitrogen atmosphere with methane and carbon monoxide, plus a vertical stack of organic haze layers above the surface. That already makes Pluto look more like a tiny cousin of Titan than a bare ice ball. But the more you look at how energy moved through this system, the stranger it gets. On most planets, when you talk about climate and temperature structure, you focus on the gases, how they absorb and emit heat. On Pluto, the solid haze particles themselves take control of a big part of the energy budget. Follow-up observations of Pluto's atmosphere using the James Webb Space Telescope showed that the upper atmosphere is colder than expected from gas physics alone, around negative 203 degrees Celsius, roughly negative 333 degrees Fahrenheit, about 30 degrees colder than earlier models predicted. The reason comes down to how the haze interacts with light. Those tiny particles absorb sunlight in the ultraviolet and visible range, then re-radiate the energy away in infrared wavelengths. In simple language, they act like little radiators suspended in the air. Instead of just warming the gas around them, they are very efficient at dumping heat to space. That means the upper atmosphere cools more than you would think if you only considered nitrogen and methane gases. In a sense, Pluto's climate is partly run by floating dust made of complex organics. The haze shapes the vertical temperature profile, changing where the atmosphere is stable, where it can mix, and how it interacts with the solar wind. So now you are dealing with a type of climate system that does not fit the standard textbook picture. You have a thin nitrogen atmosphere, a methane-driven photochemical factory making solid haze, and that haze then dominates the heating and cooling of the upper layers. It's not like Earth, with thick air and clouds of water. It's not exactly like the giant planets, dominated by deep hydrogen envelopes. It's closer in spirit to Titan, Saturn's large moon, but even there, the details differ. This is where Pluto starts to matter far beyond our own solar system. The combination of nitrogen, methane, and photochemical haze is not unique to Pluto. Titan has it. Early Earth may have had something similar when methane levels were higher. Many exoplanets we study show signs of hazes and clouds in their spectra, especially those with cooler temperatures and carbon-rich compositions. If a tiny dwarf planet at the edge of our solar system can run a haze-controlled climate, then it's reasonable to expect that some exoplanets, especially ones with high methane and nitrogen content, are doing the same thing. That matters because haze changes how a planet's atmosphere looks when you try to study it from light years away. It can mute certain spectral lines, make the planet appear cooler or warmer than it really is at certain heights, and hide the signals of molecules you're trying to detect. So, Pluto, with a surface pressure of only 10 microbar, is forcing climate scientists and exoplanet researchers to rethink some basic assumptions. Gas alone is not always the main player. Tiny, solid particles, born from photochemistry high in the atmosphere, can take over the energy balance and reshape what you see. And once you see that thin blue sky hugging Pluto's edge, one more question becomes impossible to ignore. With gravity this low and air this thin, how long can that sky actually last? What happens when the solar wind hits it? And how much of Pluto's atmosphere is quietly being stripped away into space right now? If Pluto's gravity is so weak and its air is so thin, why does it still have an atmosphere at all? Why has it not just leaked away into space completely by now? With an escape velocity of only about 1.1 kilometers per second, roughly 2,500 miles per hour, Pluto is barely able to hold on to its gas. Any molecule in the upper atmosphere that gets kicked hard enough by heat or by charged particles has a real chance of leaving forever. Up high, where the atmosphere thins into space, the gas is hot compared to the surface because it's directly exposed to ultraviolet light and to the solar wind, that stream of charged particles blowing out from the sun. Down near the ground, the pressure is around 10 microbar. Higher up, where the gas meets space, the temperature rises and the gravity is weak, so some fraction of molecules crosses the line where their random motion is fast enough to escape. That's thermal escape, molecule by molecule. New Horizons didn't just take pictures, it carried instruments designed to measure this invisible loss. SWAP, short for Solar Wind Around Pluto, and PEPSI, a particle spectrometer, were built to sniff out ions, atoms that have lost electrons, being peeled away from Pluto and picked up by the solar wind. As the spacecraft flew through the wake behind Pluto, those instruments saw nitrogen ions streaming away from the planet, forming a tail stretching tens of thousands of kilometers downstream, carried out into space. So you know Pluto is bleeding atmosphere. The next question is, how violent is that process? Is Pluto blowing off its air like a comet, or is something more subtle happening? Before New Horizons arrived, many models painted an extreme picture. They assumed the upper atmosphere would be extremely hot and extended, inflating Pluto's gas out to many planetary radii. In that scenario, the weak gravity and high temperature would drive a strong, almost comet-like outflow of nitrogen, a huge, puffy cloud being stripped away by the solar wind. From far away, you might expect something like a mini comet coma wrapped around a dwarf planet. But when New Horizons flew past and actually measured the interaction, the reality was different. It didn't see a giant unbound cloud. Instead, it found a more compact region with a boundary where the solar wind started to slow and divert, and the structured tail where nitrogen ions were being carried away. The interaction zone was there, but it wasn't enormous and diffuse. It was contained and organized. That might sound less dramatic visually, but physically it's more interesting because it means the escape is not just one simple, explosive process. The structure tells you the balance of the thermal outflow from Pluto and the pressure of the solar wind is more even than expected. The rate at which gas is leaving is lower than those early, most aggressive models predicted. You have an outflow, but you also have a controlled, shaped boundary, not a chaotic blow-off. So why should you care about the exact shape of an invisible plasma bubble at 30 to 40 times Earth's distance from the Sun? What does that really buy you? Because Pluto gives you a clean experiment in how a star's wind strips away a thin, cold atmosphere from a small body. At Pluto's orbit, the solar wind is weaker than near Earth. Its density is lower, but it is still moving at hundreds of kilometers per second. The way that wind bends around Pluto, the distance at which it is stopped, and the amount of nitrogen it manages to pick up all tell you how efficiently a stellar wind can erode a fragile atmosphere over billions of years. This is not just about Pluto. You want to understand why Mars lost most of its air. You want to know whether small exoplanets orbiting dim red dwarf stars can keep their atmospheres under much harsher winds. Pluto gives you one precise data point: a small world, mostly nitrogen atmosphere, modest loss rates, interacting with a diluted wind far from the Sun. It lets you anchor the theory and then scale it to other conditions. The immediate reaction might be, if the escape is lower than expected, maybe it does not matter. But over the age of the solar system, even a slow leak adds up. So the next question is, if Pluto has been losing atmosphere like this for 4.5 billion years, how much material has actually gone, and where did it come from? Even with a relatively modest escape rate, say on the order of hundreds of kilograms of nitrogen per second, over billions of years, the total loss can reach the equivalent of many meters to kilometers of nitrogen ice spread over the surface. That means Pluto has not just lost a little frost around the edges, it has potentially cycled a significant fraction of its volatile inventory from ice to gas to space. But you still see large deposits of nitrogen ice today, especially in Sputnik Planitia. That tells you there must be a supply side too. Nitrogen is being lost upstairs, but it is also being resupplied from below and from the surface. Sublimation from the plains, condensation in colder regions, glacial flow delivering fresh nitrogen from depth, and possibly even outgassing from the interior all help keep the atmosphere going. So Pluto's atmosphere is not a static shell. It is part of an active cycle where volatiles move between surface and sky, and the fraction is constantly peeled away into space. Over time, that tug-of-war between escape and resupply has probably reshaped the distribution of nitrogen ice, changed the thickness of glaciers, and influenced which regions remain active and which fade. Now you can see the deeper point. Pluto is teaching you how thin nitrogen-dominated atmospheres survive at all. They are fragile, yes, but they can persist if they are constantly fed by volatile ices and internal activity. The question becomes, where else does this logic apply? Think about Triton, Neptune's large moon, which also has a thin nitrogen atmosphere and volatile ices on the surface. Think about small, cold exoplanets orbiting far from their stars, or closer in around faint red dwarfs. These worlds all sit in the same category, not thick Earth-like atmospheres and not airless rocks, but something in between, where a small envelope of gas is continually threatened by escape. Pluto shows that such atmospheres can hang on for billions of years if the planet or moon has enough frozen volatiles at the surface and enough internal heat to keep cycling them. It also shows how sensitive they are to the details of stellar wind pressure, upper atmosphere chemistry, and internal supply. A slight change in any of those can tilt the balance toward collapse or persistence. So, when you look at a distant exoplanet spectrum and see signs of nitrogen, methane, or hazes, Pluto is now in the back of your mind as a template. Thin, nitrogen-dominated atmospheres do not have to vanish instantly, but they are never completely safe either. They are always negotiating with the wind from their star. And if Pluto's sky is constantly being shaved away, molecule by molecule, while new gas rises from its glaciers and maybe from its hidden ocean, what does that ongoing exchange do to the surface itself, to the patches of nitrogen, methane, carbon monoxide, and the strange red stains that cover its darker regions? How can a world this cold have weather that is basically chemistry, where a change of just a few degrees shuffles entire ice caps around the globe? When New Horizons looked not just at the shapes of Pluto's terrain, but at the actual substances on the surface, it found that Pluto was covered in a patchwork of different ices that move, react, and even change the local climate. The first thing to get clear is that not all ice on Pluto is the same stuff. When you look at Sputnik Planitia with spectral instruments, which break light into its component colors and fingerprints, you see that this huge basin is dominated by nitrogen ice, solid N2. Mixed into it are noticeable amounts of carbon monoxide ice and methane ice, CO and CH4. That whole area really is a massive nitrogen glacier, with other volatiles dissolved or mixed in. Methane behaves differently. It is not just confined to Sputnik Planitia. Methane ice is more widespread over the globe and tends to concentrate in higher latitudes and in bright, elevated regions. So you have this contrast, a low, bright basin rich in nitrogen and carbon monoxide, and then other bright patches and caps at higher latitudes that are richer in methane. Carbon monoxide appears in patches too, often associated with the nitrogen plains but not spread uniformly. So when you look at Pluto, you're not seeing a uniform frost. You're seeing a planet-scale pattern in three main exotic ices: nitrogen, methane, and carbon monoxide. The obvious question is, what is sorting them? Why does nitrogen pile up in one place, methane in another, and carbon monoxide in specific patches? The key is that at Pluto's temperatures, around 40 to 60 Kelvin, a shift of just a few degrees is a big deal. At those temperatures, the vapor pressures of nitrogen, methane, and carbon monoxide are extremely sensitive to temperature and are very different from each other. Vapor pressure here just means how easily a solid will turn into gas. Nitrogen is the most volatile of the three. It turns to gas more easily. Carbon monoxide is similar. Methane is a bit more stable as a solid at a given temperature. This means that when one region of Pluto warms by just a couple of Kelvin during its long season, nitrogen and carbon monoxide will start to sublimate there and enter the atmosphere, while methane might remain frozen. That gas can move with the winds, then condense and refreeze wherever conditions are slightly colder. Over years to centuries, that constant slow movement moves ices around. Regions that are good cold traps build up thick nitrogen deposits. Slightly warmer areas, still brutally cold by Earth standards, may lose nitrogen but keep methane. The whole planet starts to behave like a very slow planet-scale separation, driven by small temperature differences. The result is bright nitrogen-rich plains, methane-rich caps and ridges, and specific zones where carbon monoxide tags along with nitrogen. But you still have another ingredient painting Pluto's surface that changes the rules again: the red stuff. When you look at dark regions like Cthulhu Macula along the equator, you see they are coated with a deep reddish-brown material. These are tholins, complex organic solids created when energetic radiation, ultraviolet light, and charged particles hit the surface ices and break them apart and recombine them into heavier molecules. These tholins are not icy white. They are dark and absorb a lot of sunlight. That does two things. First, they lower the albedo, the reflectivity of the surface, meaning more incoming solar energy is absorbed rather than bounced back to space. Second, that extra absorption warms the local surface slightly compared to nearby bright, icy terrain. Remember, on Pluto, a small warming of a few Kelvin can decide whether nitrogen stays frozen or starts to sublimate. So, in dark tholin-covered terrains, nitrogen and maybe carbon monoxide can be driven off more easily, while methane may hang on longer. Over time, that means organics don't just color the surface, they actively steer where volatile ices can survive. The chemistry of the surface and the chemistry of the atmosphere are now directly linked to the geology and the energy balance. You can see the combined effect right on Sputnik Planitia itself. In high-resolution images of its western margin, New Horizons spotted patterns that look like dunes, aligned in rows, with lighter-toned ridges and darker streaks downwind. Models suggest these dunes are made of small methane ice grains, not sand like on Earth, moved by winds of only a few meters per second, on the order of 10 kilometers per hour, a light breeze here. In Pluto's low gravity and thin air, those modest winds are still strong enough to pick up and push methane particles across the nitrogen plains, building real dune fields. The darker streaks in between may be regions where either the grains are absent or where darker material has been exposed or concentrated by the same winds. So in one basin, you have nitrogen flowing slowly as a glacier, methane collecting into frost and dunes, carbon monoxide mixed in, and winds strong enough under Pluto's conditions to rearrange the grains. All of that is happening in temperatures around minus 230 to minus 210 degrees Celsius, minus 380 to minus 340 degrees Fahrenheit. This is the point where you have to step back and see what Pluto is really telling you. On Earth, you are used to thinking of climate as mostly sunlight plus water plus air. On Pluto, climate is being run by a three-ice system: nitrogen, methane, and carbon monoxide, plus solid organics. Each ice has different volatility. Each responds differently to small temperature changes. The tholins change how much sunlight is absorbed. The haze in the atmosphere changes how heat is radiated away. All of these pieces interact in feedback loops. Bright nitrogen plains reflect sunlight and stay cooler, promoting more nitrogen deposition. Dark tholin-stained terrains absorb more heat, drive off nitrogen, and maybe let methane dominate. Methane and nitrogen ices switch places over long seasons. The atmosphere thickens and thins as ices sublimate or freeze out. Winds move methane grains into dunes, which can further change how the surface interacts with sunlight. So Pluto does not let you treat surface geology and atmosphere as separate chapters. The chemistry of the ices and organics is part of the climate engine. You have a compact alien system where composition, reflectivity, temperature, and atmospheric pressure are locked together. And once you realize that Pluto's strange patchwork of nitrogen plains, methane caps, carbon monoxide streaks, and red tholin stains is actually a climate machine, you have to confront one more puzzle. If chemistry and climate are this tightly linked, why do some regions look frozen in deep time, packed with ancient craters, while others are so fresh they have almost no craters at all? And what does that say about how long Pluto has been active? Why does Pluto look like two different worlds glued together, one covered in ancient scars, the other looking almost brand new? When you line up New Horizons images, the age contrast on this tiny dwarf planet is one of the biggest shocks in the whole mission. In some regions, especially along the dark equatorial belts like Cthulhu Macula, the surface is packed with craters. You see impact structures, tens to hundreds of kilometers across, overlapping, worn down, but clearly very old. When you run the statistics on crater sizes and densities, you get ages of around 4 billion years. That means those terrains have been sitting there, basically unchanged since the early solar system, only modified by other impacts and slow space weathering. Now compare that to Sputnik Planitia, right next door in planetary terms. The giant nitrogen basin is almost completely smooth. When you zoom in, you have to work to find even a few small craters. The crater counts there give ages under about 100 million years, and some patches could be as young as 10 million years or less. On geological timescales, that is very recent. You are looking at something that has been active in what you would reasonably call Pluto's current era, not just in some distant past. So on one hemisphere, you have surfaces recording almost the entire age of the solar system. On another, you have surfaces that were effectively reset in the last few percent of that time. The paradox is clear. If Pluto were truly dead, you would expect old and cratered almost everywhere. Instead, you get a sharp contrast between frozen history and freshly repainted terrain. The only way to reconcile that is to accept that Pluto has been resurfacing itself in specific places. The active processes you have already seen on Sputnik Planitia provide the mechanism. Convection in the nitrogen ice brings new material up from depth and drags old, cratered surfaces down. Glacial flow slowly spreads and rearranges ice, burying old craters under fresh deposits. Sublimation pits form where nitrogen turns to gas and escapes, then refreezes elsewhere, etching and filling the surface. In regions influenced by cryovolcanism, flows of water-rich or volatile-rich slush could have covered older terrains. None of these processes are fast, like eruptions or landslides on Earth. They can run at centimeters per year, or even slower. But over 10 to 100 million years, that's enough to erase the crater record. Wherever the nitrogen glaciers creep, the surface is continually repaired, and the crater clock is reset. Where they do not reach, or where internal activity is weaker, ancient craters remain, recording deep time. So you get this patchy history where age is not just a function of latitude or longitude, but how strongly each region has been plugged into Pluto's internal machinery and volatile cycles. That alone is a huge shift from the old picture of a uniformly dead ice ball. But the surface tells an even deeper story when you look at the giant fractures cutting across it. New Horizons mapped enormous chasms and trough systems on Pluto, some hundreds of kilometers long and several kilometers deep. These are not random cracks from local impacts. They look like graben, structures where blocks of crust drop down between parallel faults because the surface is being pulled apart. That's extensional tectonics on a global scale. What could be stretching Pluto's crust like that? It fits very well with the underwater ocean story. As the interior ocean slowly freezes, water turns to ice and expands. That expansion pushes outward on the overlying shell. Over long times, the solid outer layers can't stretch smoothly, so they fracture, creating chasms that can reach several kilometers in depth. These huge faults are like scars from Pluto's interior growth and cooling. The important point here is that you're seeing tectonic evidence for internal evolution, not just random cracking. The planet has changed shape slightly as its interior structure evolved, and the crust has broken to accommodate that change. That's not the behavior of a body that froze solid early and then just sat there. Charon, Pluto's largest moon, backs up this story when you examine its surface in the same way. Overall, Charon's terrain looks less varied than Pluto's, more dominated by water ice and lacking Pluto's big volatile plains. But it still shows a mix of very old, heavily cratered regions and younger, resurfaced patches. There's a huge belt of chasms and fractured terrain encircling much of Charon, with canyons deeper than the Grand Canyon on Earth. Those features point to a similar process, an interior that once had enough heat to support an ocean, or at least a layer of soft, partially melted ice, followed by cooling and freezing that caused the outer shell to crack and expand. Charon's resurfaced areas with smoother plains and fewer craters also hint that material has erupted or flowed across the surface at some stage, erasing older impacts. So when you compare crater count and tectonic features on Pluto and Charon together, you get a consistent picture. Both bodies have very old surfaces in places. Both also have younger terrains where geology has rewritten the record. Both show large-scale extension, consistent with interior water layers freezing and expanding. That means both have experienced real internal heating and tectonic behavior, not just passive impact gardening. This directly attacks the old, simple rule of thumb that small icy worlds cool down quickly and then die. The standard narrative used to say that once a body is below a certain mass, it can't maintain internal heat long enough to stay geologically active. It should freeze solid in a few 100 million years, maybe show a little residual activity and then shut down permanently. Pluto and Charon are telling you that this is wrong, or at least incomplete. With the right composition, with a rocky core that contains enough radioactive elements, and a thick enough insulating shell of ice and volatiles, even relatively small worlds can stretch out their heat budget over billions of years. They can run slow, deep processes that build mountains, drag glaciers, sustain oceans under ice, and crack their own crusts open long after you expected them to be inert. That has major implications, not just for them, but for the whole population of similar bodies. If Pluto and Charon can stay active for billions of years, then other Kuiper Belt objects of similar size and icy moons around giant planets are not automatically dead just because they are small. Some of them might still be evolving inside, even if we have not seen them up close yet. And once you accept that both halves of the Pluto-Charon system are long-lived, evolving worlds instead of cold leftovers, you have to ask the next question. If Pluto is this complex, what does its partner really look like up close? How did Charon break, stain, and reshape itself while locked in this binary dance? How can the world right next to Pluto look so different and still tell the same deep story underneath? When New Horizons turned its cameras from Pluto to Charon, it was not just checking off the big moon. It was looking at the other half of a system that formed together, evolved together, and then clearly took two very different paths. Charon is big, especially for a moon. It is roughly 1,212 kilometers across, about 750 miles, so around half of Pluto's diameter. Put Pluto and Charon side by side, and together they would only just stretch across the continental United States. But in terms of mass ratio and size, this is much closer to a double planet than a classic planet-moon setup. Charon is not a small sidekick, it is a full world in its own right. The first thing you notice is the surface composition, where Pluto is coated with exotic ices, nitrogen, methane, carbon monoxide. Charon is dominated by water ice. Spectral data make that very clear. You do not see huge nitrogen plains or methane caps. You see a crust that behaves more like cold, hard water rock with only traces of volatiles. That already explains part of the difference. Pluto can run a nitrogen atmosphere and glacier system. Charon cannot. It simply does not have the same stockpile of easily evaporated ices at the surface. But no nitrogen plains does not mean nothing interesting. In fact, Charon's surface looks like it's been physically torn open. One of the most striking features New Horizons revealed is a belt of enormous canyons and fractured terrain that wraps around much of the moon. Some of these chasms are more than 1,000 kilometers long, over 600 miles, and estimates for their depth reach 7 to 9 kilometers, up to around 4 to 5.5 miles. That's deeper than the Grand Canyon and on a much smaller body. These are not small cracks, they are giant scar lines where the crust has clearly been pulled apart. You see ridges, cliff faces, and long depressions, classic textbook signatures of extensional tectonics, where the surface is being stretched rather than squeezed. It looks like Charon's outer shell has been forced to expand and split, leaving a global belt of broken crust as evidence. Then, as you move your view toward the North Pole, you hit something that almost looks out of place. Charon's North Polar region is coated in a dark reddish cap. It was striking enough that the team nicknamed it Mordor Macula early on. That color does not come from water ice alone. It comes from tholins, complex organic material, very similar in nature to the red stains on Pluto, but formed in a different way. Here's the likely chain of events. Pluto's thin atmosphere leaks nitrogen and methane over time. Some of those escaping molecules don't go straight into space. Instead, they enter orbits that intersect Charon or drift into its path. When Charon's North Pole is in its long winter, locked in darkness for decades, it becomes a cold trap. Escaping nitrogen and methane from Pluto can freeze out there as a very thin frost. Then, even in the dark, radiation from space, ultraviolet from scattered sunlight, and charged particles slowly cook that frost, breaking the simple molecules and recombining them into heavier organics, the same kind of tholins you see elsewhere in the outer solar system. Over long times, that process builds up a thin but persistent layer of dark, reddish material. So Charon's polar cap is basically Pluto's lost atmosphere, caught and processed on the neighbor's pole. That's an important point. The binary system is exchanging material. Pluto's activity does not stop at its own exobase. Some of it ends up painting Charon. So you have two huge clues right away, a fractured crust telling you Charon has been stretched, and the polar stain telling you it has been interacting with Pluto's escaping gases. The next step is to connect those fractures to what was happening inside Charon, not just on its surface. The pattern of chasms combined with smoother plains in some regions fits very well with an internal ocean freeze-out story. The idea is this. Early in its history, Charon likely had enough heat from the energy of the giant impact that formed the Pluto-Charon system and from radioactive decay in its rocky interior to support a layer of liquid water, or at least very soft, warm ice beneath a colder crust. As that interior layer slowly cooled and froze over time, the phase change from liquid to solid water caused an expansion. Remember, water ice takes up more volume than liquid water at the same pressure. That expansion pushes outward on the shell. On a small body with a brittle outer layer, the only way to accommodate that is to crack. The crust splits, blocks drop down or rise up, and long canyons open. The resurfaced plains you see in some regions may be cryovolcanic or warm ice flows that filled low areas when the interior was still partially molten. The heavily cratered highlands represent the older, unmodified crust. So Charon's surface is basically a frozen record of its internal evolution, the lower half of the world pulled apart by a freezing ocean or deep warm layer, the upper region smeared with organics delivered by Pluto's leaking nitrogen and methane. Where Pluto expressed its internal activity with nitrogen plains, mountains of water ice, and possibly cryovolcanoes, Charon expressed it with massive faults and resurfaced patches written in water ice. This is where the Pluto-Charon system becomes more than just a set of interesting pictures. Together, they form a natural experiment in binary evolution. Both bodies probably formed from the same giant impact, early in solar system history, like a scaled-down version of the event that gave Earth its moon. They started with similar bulk compositions, rock and ice mixed, but because Pluto is slightly larger and able to hang on to volatiles, and because of differences in how heat was stored and released, the two worlds diverged. Pluto kept enough nitrogen and methane to build an atmosphere, run glaciers, and possibly maintain a long-lived subsurface ocean. Charon lost most of its easily evaporated ices from the surface, ended up with a water ice-dominated crust, and froze out its internal ocean more completely. Pluto hides much of its tectonic history under deposits of nitrogen, methane, and haze-driven chemistry. Charon wears its tectonic story openly as great belts of canyons and fractures. For planetary science, that's gold. It means you can study how two similar-sized icy bodies with shared origin and shared environment can end up with very different expression of internal heat and volatile budgets. That directly feeds into how you think about other binary or closely paired systems, whether in the Kuiper Belt, around giant planets, or around other stars. And once you see that even Charon, the airless companion, has been fractured by internal changes and painted by Pluto's escaping atmosphere, it becomes harder to treat the smaller moons in the system as simple rubble. If the big pair is this dynamic, what kind of chaos do you get from the tiny, bright, fast-spinning shards orbiting farther out? How do you get four tiny moons that look like they should be boring rubble, but instead act like they are trapped in a gravitational washing machine? When New Horizons finally resolved Styx, Nix, Kerberos, and Hydra, the surprise was not just that they were there, but how odd they are, both in shape and in motion. Start with size and shape, because that already breaks the classic moon picture. Hydra and Nix are each only around 40 kilometers across at their longest dimension, roughly 25 miles. Styx and Kerberos are even smaller, around 10 kilometers, about 6 miles. None of them are spherical. They are elongated, lumpy bodies, more like stretched potatoes or joined chunks than anything that has relaxed into a smooth ball. At these sizes, their gravity is too weak to pull them into round shapes, so whatever shape the collisions and accretion left them with is roughly what they keep. Despite that, their surfaces are not dark, dirty ice like you might expect from random Kuiper Belt debris. Their albedos, their reflectivities, are high, in the range of about 50 to 90%. That means they reflect half to almost all of the light that hits them, more like fresh snow than like the dark, charcoal-colored surfaces of typical small Kuiper Belt objects. Spectra show they are dominated by clean water ice. So even though they are tiny, they are surprisingly bright. That combination is already strange. Tiny, irregular, but very reflective. It fits with the idea that they formed from clean, icy debris thrown out when the Pluto-Charon system formed in a giant impact. Over time, micrometeorite impacts and space weathering usually darken surfaces. But here, either the starting material was very bright and the darkening has been slow, or impacts keep exposing fresh ice underneath. If these were ordinary moons in a simple planet-moon setup, you might expect them to be tidally locked, always showing the same face to Pluto, the way our moon shows one face to Earth. But when New Horizons measured their rotation, the behavior was completely different and much more chaotic. These small moons spin rapidly, with rotation periods of hours, not days, and their spin axes are not stable. They tumble. Their poles wander. Their orientation changes over time. The reason is the complex gravitational field created by the Pluto-Charon binary. Instead of orbiting one dominant central mass, these moons orbit a pair of bodies spinning around the common center of mass outside Pluto. The gravitational pull they feel varies in direction and strength as they move, and that constant torque prevents them from settling into a simple locked state. You can think of it in simple terms like this. Our moon sits in a relatively stable gravitational gradient, so over time, tidal forces slowed its spin and locked one side toward Earth. Around Pluto and Charon, the gradient keeps changing as the pair spins. For tiny, irregular bodies like Nix and Hydra, that means no stable lock. The result is rotation that looks more like an object thrown in the air than a carefully aligned moon, fast and wobbling, not synchronized. Next you ask, if their dynamics are so wild, what about their surfaces? Are they young and constantly reshaped, or old and preserved? When scientists looked at crater counts on Nix and Hydra, they found that their surfaces are heavily cratered. The densities of those craters match ages of roughly 4 billion years. That means these small moons have very ancient crusts. Unlike Pluto's Sputnik Planitia or the younger regions on Charon, there is no clear sign that internal processes have resurfaced them significantly. No giant glaciers, no evidence of cryovolcanic flows, just impact after impact layered on top of each other. So you get an interesting combination. Dynamically chaotic, but geologically quiet. They have been spun and twisted by the gravitational field for billions of years, but their surfaces still record the early bombardment of the solar system relatively unchanged by internal heating. Put all of that together, and you get a very specific lesson. These small moons are not just mini versions of ordinary satellites. They are what you get when you put tiny, icy fragments in orbit around a binary planet instead of a single body. Their high albedo points to clean water ice and an origin in a giant impact. Their odd shapes reflect their low gravity and collisional history. Their chaotic spins come from being tugged by two large neighbors instead of one. Their cratered surfaces tell you they have not been melted or seriously reworked from inside. So that has broader stakes. When you think about satellites in binary systems, whether in our Kuiper Belt or in exoplanet systems with binary planets or close massive pairs, you can't just copy-paste the one planet, one moon, tidal lock mental model you get from Earth and its moon. The dynamics can be more complex, the spins can be chaotic, and the long-term behavior of small bodies in those systems can be very different, even if their sizes and compositions are similar. It also underscores how intertwined this whole system is. Pluto and Charon set up the gravitational environment. The giant impact that probably formed them also likely produced the debris that built Styx, Nix, Kerberos, and Hydra. Pluto's escaping atmosphere paints Charon's pole. The small moons orbit in this shifting field, bright shards that spin unpredictably while carrying very old scars. Once you see that even these tiny pieces are behaving in ways you don't see around single planets, it raises one more question you can't skip. If the whole Pluto-Charon system is this dynamically and chemically rich, what happens when you zoom out again to the scale of Pluto's orbit and year and ask how all of this plays out over the extreme 248-year seasons, with nitrogen, methane, and haze all cycling through that long, tilted orbit? How do you talk about seasons on a world where one winter night can last longer than your entire country's history? Pluto orbits the Sun once every 248 Earth years, and its axis is tilted by about 120 degrees. That tilt is more than sideways, so one hemisphere can be aimed toward the Sun for decades, while the other is plunged into decades of darkness. That means Pluto's seasons are not a neat four-part cycle like on Earth. They are long, slow shifts. A region can spend a huge chunk of time in permanent day, then slowly slide into permanent night over decades. During that long day, temperatures rise by only a few Kelvin, but out at Pluto, a tiny temperature change is enough to completely reorganize where the ices and the atmosphere go. Start with the basics, because this is the backbone of Pluto's weather. The surface is covered in nitrogen and methane ices, especially in places like Sputnik Planitia and at certain latitudes. When that region leans toward the Sun for its long summer, the extra sunlight warms the surface just enough that nitrogen and methane start to sublimate. They go straight from solid to gas. The thin atmosphere thickens, pressure goes up by factors of several, and you get more gas to move around the globe. That gas does not stay put. It travels. Winds carry nitrogen and methane to colder regions, often at higher latitudes or lower-lying basins that are in shadow or just receive less energy. There, the gas cools and refreezes as frost or thin ice layers. When the seasons slowly flip, the process reverses. What was a source can become a sink and vice versa. Over a full Pluto year, you're cycling volatiles between hemispheres, moving material from one side of the planet to the other. Sputnik Planitia is central in this cycle. It sits low, it is filled with nitrogen, and it's cold, so it acts as both a source and a receiver. When it's sunlit, it releases nitrogen into the atmosphere. When conditions shift, it can collect nitrogen back. It's a kind of planetary scale cold trap and reservoir. The heart on Pluto's surface is also the heart of its nitrogen cycle. This constant sublimation, transport, and refreezing is what we really mean when we say Pluto has weather. There are no rainstorms, no liquid rivers, but there is a continuous exchange of material between surface and sky. The pressure at the ground may only be about 10 microbar, around 100,000 times less than at sea level on Earth, but that is still enough gas to carry momentum, to move frost, and to respond to pressure differences. Now look at the winds, because they are not random. Climate models that plug in Pluto's topography, the properties of nitrogen ice, and the long seasons show that Sputnik Planitia does more than just store volatiles. It drives circulation. When the sun warms the basin, nitrogen sublimates, and the pressure over the plain rises slightly. As the gas cools near the edges or flows out over higher ground, it creates horizontal pressure gradients. Air tends to flow from high pressure to low pressure, so you get near-surface winds that run along the basin and out onto the surrounding terrain. Those models show that these winds tend to blow westward along the equator, opposite Pluto's eastward rotation. In some seasons, wind speeds near the surface could reach tens of meters per second, on the order of 30 to 50 kilometers per hour, around 20 to 30 miles per hour. That may sound like a moderate breeze here, But on Pluto, with low gravity and tiny grains of methane and nitrogen frost, that's enough to sculpt dunes, build drifts, and carve wind streaks. The dunes seen on the edge of Sputnik Planitia line up with these predicted wind directions. So you have a frozen heart that literally drives global winds through the simple act of turning nitrogen on and off between solid and gas. That is a very direct connection between geology and atmosphere. Now add the haze. You already saw that Pluto's sky is filled with thin layers of hydrocarbon haze, formed when ultraviolet light hits methane high above the surface. Those particles are not just passengers. They affect how the atmosphere gains and loses heat. The hydrocarbon particles scatter blue light, which is why Pluto's limb looks blue in backlit images. But more importantly, they absorb sunlight across a range of wavelengths and then re-emit that energy as infrared radiation. The James Webb Space Telescope observations showed that Pluto's upper atmosphere is cooler than you would expect if you only considered the gases present, by roughly 30 degrees Celsius, about 54 degrees Fahrenheit. Instead of following a simple gas-only temperature profile, the upper layers are cooled because the haze is so efficient at radiating heat away into space. That means the vertical temperature structure of Pluto's atmosphere is not set just by gas composition and solar heating. It's set by a balance between solar input, gas cooling, and haze cooling. The haze acts like a built-in radiative engine, adjusting how heat is distributed with height. That affects how the air can mix vertically, where temperature inversions happen, and how the atmosphere couples to the surface. Put this together and you get a very stripped-down climate system. Pluto has almost no air by Earth standards, no liquid oceans on the surface, no forests, no cloud decks of water. It has 10 microbar of mostly nitrogen, a stock of frozen nitrogen and methane spread over the ground, one giant cold basin that breathes in and out with the seasons, and a high-altitude haze that controls cooling. From those few ingredients, you still get winds, weather patterns, pressure changes, and the long-term volatile cycle. This is the key point. Climate does not require a thick atmosphere like Earth's. It does not require rainfall or large bodies of liquid water on the surface. It just needs energy gradients, materials that can change phase, and enough time for those changes to matter. On Pluto, the gradients are tiny in absolute terms, a few Kelvin here and there, but the volatiles are so sensitive that those small differences move glaciers and reshape ice caps over centuries. If a dwarf planet at negative 230 degrees Celsius with almost no air can run a recognizable climate engine from nothing but nitrogen, methane, and haze, what does that do to your picture of which worlds are interesting enough to study? You are forced to admit that even very thin, exotic atmospheres can support real weather and long-term cycles. And that brings you to a very awkward tension. You have a world with real geology, active glaciers, possible oceans, winds, seasons, and climate physics that matter for exoplanets. Yet, during the very mission that revealed all this, humanity officially pushed Pluto down into the dwarf planet box. So the next question is obvious. How do we manage to demote one of the most complex small worlds we have ever seen? And what does that say about how we decide what counts as a planet in the first place? How do you take a world that clearly behaves like a planet and tell everyone it doesn't count right before you finally see it up close? That is exactly what happened to Pluto. In August 2006, while New Horizons was still in deep space on its way out, the International Astronomical Union voted to reclassify Pluto as a dwarf planet. The argument was orbital, not geological. Pluto is round, yes. It orbits the sun, yes. But it does not clear its orbit of other bodies. It shares its region with many Kuiper Belt objects and is locked in a resonance with Neptune instead of dominating its zone the way Earth or Jupiter does. On paper, the new rule said, to be a planet, you must orbit the sun, you must be massive enough to pull yourself into a roughly spherical shape, and you must have cleared your neighborhood. Pluto failed that third test, so it was moved into a new box, dwarf planet. The physics of Pluto did not change that day. Its mass stayed the same, its radius stayed the same, its orbit stayed the same. But the label changed how people thought about it. A lot of the public started imagining Pluto as less real, less worthy of attention, more like an upgraded asteroid than a serious world. Then New Horizons arrived in July 2015 and blew that perception apart in a single flyby. Remember what we had before: fuzzy dots, blurry brightness patterns, speculation. After closest approach, suddenly you had a world in front of you with detailed maps, mountains 3 to 4 kilometers high, 10 to 13,000 feet, made of water ice, a giant nitrogen glacier in Sputnik Planitia, roughly 1,400 by 1,200 kilometers in size, with convection cells and dunes, evidence for a deep subsurface ocean under the crust. Huge chasms hundreds of kilometers long, a thin, layered blue atmosphere with haze up to 200 to 300 kilometers high, an active volatile cycle, winds, seasons, and a big companion, Charon, that is half its size, forming a true binary system. That is not how a footnote world behaves. That is how a frontier world behaves. So now you're forced to ask a sharper question. What do you really mean when you say planet-like? If you look at Pluto geophysically, by its internal structure and activity, it checks many of the boxes scientists care about when they study planets. It is in hydrostatic equilibrium, meaning gravity has pulled it into a round shape. It is differentiated into a rocky core, an ice mantle, and a volatile rich surface. It likely has or had a liquid water ocean. It shows ongoing or recent geological activity, from glaciers and possible cryovolcanoes to tectonic fractures. From that perspective, Pluto sits much closer in behavior to Mars or the icy moons like Europa and Enceladus than it does to small, irregular asteroids. It's a small world, yes, but a real world. The demotion pushed people to separate two different things that had been tangled together: orbital dynamics and intrinsic complexity. The IAU definition is about how an object behaves in its orbit. Planetary scientists often care more about what is happening inside and on the surface. That disagreement is why the "is Pluto a planet" argument never really died. It's not just nostalgia. It's a fight over which criteria matter more: how clean your orbit is, or how much world building is going on inside the object. New Horizons poured fuel on that fire, because once you see glaciers and mountains and potential oceans, it gets much harder, emotionally and scientifically, to shrug off Pluto as a minor bit of debris. Then there's another twist. Pluto didn't turn out to be a strange exception. It turned out to be the first well-mapped example of an entire class of objects that we now know are common. In the years leading up to and following Pluto's reclassification, astronomers found several other bodies of similar size in the outer solar system: Eris, Haumea, Makemake, and more. Many of these objects are on the order of 1,000 kilometers across, or larger. Some are slightly bigger than Pluto. They live in the Kuiper Belt and beyond, a huge region of icy bodies beyond Neptune. That region is essentially a second main belt like the asteroid belt, but made mostly of ices and rock mixtures instead of mostly rock and metal. Pluto sits at the inner edge of that population as the first close-up case. New Horizons showed that at least one Kuiper Belt dwarf planet is geophysically complex. It made it very hard to argue that the others are just simple ice rocks without interesting interiors. Suddenly, each named object in that list is not just a number. It's a candidate for its own glaciers, its own fractures, its own internal ocean, depending on its exact size and composition. In that sense, New Horizons did something bigger than save Pluto. It opened the door to the Kuiper Belt as a serious target for planetary science. It said, this is not a junkyard, it's an outer planetary system made of smaller worlds. The label dwarf planet may sound like a downgrade, but scientifically it marks a whole class that needs attention, not one oddball that got kicked out of the club. This is why the stakes of the planet debate go beyond school posters. Names affect where you point telescopes, how you design missions, and how you talk about exoplanets. If you treat objects in the Pluto size range as second tier by definition, you might underestimate how many of them could be geologically active, have atmospheres, or even hide oceans. When you look at exoplanet catalogs, you see many worlds roughly Pluto-sized to Mars-sized, orbiting far from their stars, where temperatures are low enough for nitrogen, methane, and water ices. Pluto provides a template for what one of those worlds can do. Whether you call Pluto a planet, a dwarf planet, or something else, the geology is what sets the expectations. So here's the bottom line. Labels are mostly human convention. The rock and ice do not care what you call them. Pluto's demotion did not change its mountains, its glaciers, its winds, or its possible ocean. New Horizons forced everyone to confront a harder truth. Small, distant, icy worlds are not automatically simple. They can rival Mars in complexity, and they matter for how you interpret almost every cold, mid-sized exoplanet we discover. And if a dwarf planet can humble us this much, you have to ask one last question about New Horizons itself. What happens when you push even farther, past Pluto, into the deep Kuiper Belt and use the same spacecraft to peek at one of the most primitive building blocks of the solar system, and to keep listening from more than 60 astronomical units away? So what do you do with a spacecraft after it has already blown up everything you thought you knew about a planet and is still racing outward into the dark? You point it at something even more primitive, and you let it tell you how planets were born in the first place. After Pluto, New Horizons was not done. Mission Control steered it toward a small Kuiper Belt object then known as 2014 MU69, later named Arrokoth. On the first day of 2019, it flew past this tiny body and saw something no probe had ever seen up close before, a pristine building block from the early solar system. Arrokoth turned out to be a contact binary, two lobes stuck together, not merged into a single round object. The larger lobe is roughly 36 by 27 by 20 kilometers, about 22 by 17 by 12 miles. The smaller one is around 21 by 20 by 15 kilometers, about 13 by 12 by 9 miles. The shapes and the gentle neck connecting them tell you something important. These two pieces came together slowly, at low speed, not in a violent smash. They likely formed from the same patch of the original solar nebula, collapsed as a cloud of dust and ice, then spiraled together under mutual gravity and touched gently enough to stay intact. That is exactly the kind of process models predict for planetesimal formation, but here you are seeing the end product directly. Arrokoth is about as close as you can get to a fossil of the original building blocks that later merged into full planets. It is the most primitive object any spacecraft has ever visited, and it looks like the early solar system frozen in place. So after you've flown past Pluto and Arrokoth, is New Horizons just an empty shell coasting outward, or is it still a working science mission? As of 2025, it's more than 60 astronomical units from the Sun. 1 AU is the Earth-Sun distance, so you're talking over 60 times that, well beyond Pluto, heading into the deep Kuiper Belt. It's still moving at about 13.7 kilometers per second, around 49,000 kilometers per hour, about 30,000 miles per hour, and its radios are still on. From out there, it can measure the density and properties of dust grains in the Kuiper Belt, count how many tiny impacts it experiences, and map the structure of the distant solar wind and the heliosphere, the bubble carved out by our sun's magnetic field. It tells you how the solar wind changes with distance, how energetic particles behave at the edge of the system, and how the local interstellar environment may look when the sun's influence fades. Together with the Voyager spacecraft farther out, New Horizons gives you a multi-point view of the outer heliosphere, something you cannot get from Earth. But you might ask, all of this is interesting for solar system science. Why should people who study exoplanets care what one probe saw at one small world? Because Pluto is not just Pluto, it's a template. A roughly 2,400 kilometer class object with a nitrogen atmosphere, hydrocarbon haze, volatile ices, and possibly a subsurface ocean sitting tens of astronomical units from its star is not unique. That size and temperature range appears again and again in exoplanet catalogs in the form of cold super-Earths, mini Neptunes with large ice fractions, and distant low irradiance planets around other stars. The physics New Horizons uncovered at Pluto, volatile cycles of nitrogen and methane, haze-driven climate, slow atmospheric escape, long-lived subsurface oceans under thick ice shells, all of that scales. It changes how you interpret a remote spectrum that shows strong haze signatures or hints of nitrogen and methane. It tells you that even a thin atmosphere interacting with exotic ices can drive real climate. It warns you that haze can cool an upper atmosphere and mask certain spectral lines. Every time you look at a cold, mid-sized exoplanet with an atmosphere, the Pluto data is now part of the background model, whether you like that or not. If one high-speed flyby changed that much, the obvious next step is, what are we missing by not staying? A flyby is a snapshot, a single frame. It shows you that Sputnik Planitia is convecting now, that nitrogen dunes exist now, that the atmosphere has haze layers now, that the fractures and mountains are there now. What it cannot show you is how fast those convection cells evolve, how the ice caps and atmospheric pressure shift over Pluto's long seasons, or exactly how thick that subsurface ocean really is. To answer those questions, you need an orbiter. You would want a spacecraft that can break into orbit around Pluto, not just pass once. It would carry radar instruments to sound down through the ice shell and map the ocean's thickness. It would carry high-resolution cameras to repeatedly image Sputnik Planitia, watching the convection patterns in glaciers change over years. It would measure the atmosphere's pressure and composition across different seasons, track the haze, and watch how the distribution of bright and dark ices moves with time. It would also orbit long enough to build a detailed gravity field map, tightening your models of Pluto's internal structure, and it would be able to systematically map Charon and the small moons from all angles. Technically, getting an orbiter there is hard. You need a lot of energy to both reach Pluto and slow down. You probably need advanced propulsion or clever gravity assist paths, and you need reliable nuclear power for instruments that will operate in weak sunlight for decades. But after New Horizons, Pluto moved from last stop, maybe not worth it, to top-tier target for any future outer solar system exploration roadmap. The science return from watching an active dwarf planet and its binary companion over time would be enormous. Step back one level and ask what all of this has really done to your picture of the solar system. Before New Horizons, it was easy to divide things into neat categories. Big planets that are active, small stuff that is dead debris. Pluto, Charon, Arakoth, and the Kuiper Belt data make that division look lazy. You now see a continuum. On one end, giant planets and large rocky worlds with thick atmospheres and obvious geology. On the other end, tiny, irregular chunks. In between, a whole spectrum of mid-sized icy bodies and dwarf planets that can carry oceans, drive glaciers, run atmospheres, and keep internal heat going for billions of years. Pluto sits right in that middle zone and proves the point. At around minus 230 degrees Celsius, roughly minus 380 degrees Fahrenheit, nearly 5.9 billion kilometers from the sun, it still runs nitrogen glaciers, builds mountains of water ice 3 to 4 kilometers high, drives winds that shape dunes, and may hide a global ocean under its crust. It orbits as part of a complex binary with Charon, paints its neighbor's pole with escaped gases, and sits inside a system with chaotic small moons and a shared origin in a giant impact. What NASA found on Pluto did more than shock scientists. It forced them to redraw the mental map of what a living world can be. Activity is not reserved for big, warm planets close to their stars. It can exist on small, cold, distant bodies powered by slow internal heat and volatile chemistry. The solar system is not neatly divided. It is full of worlds in between. And the next time you see a cold, mid-sized exoplanet on a chart, you will not be able to write it off as just a frozen rock, because a demoted dwarf at the edge of your own system already proved that assumption wrong. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.